Hello, we are Team Fireball. From left to right, Justin Pettingill, Joey Gibson, and Matthew Nichols. We are from the lab section beginning at 12:30 p.m. The goal of this project was to create a device that organizes HDPE filament as it is produced by the senior design team's extruder. Shown here are the senior design team's extruder, the filament produced by the extruder, and the ideal method of organizing the filament. Our group chose to use a standard size spool for the MakerBot replicator to collect the material coming from the extruder. We did this simply so that this spooled material could be used with any 3D printer. Using the specifications given to us by the senior design team in a math model, we were able to select a DC motor that was suitable for turning a fully loaded spool of HDPE filament. Factors considered were torque output, current flow ratings, and angular velocity. After selecting a suitable motor for our design, we began designing a component of the system to distribute the filament evenly across the spool as it was turning. Initially, we began with a complex design involving a worm gear and a track. After deciding that this design would have way too many moving parts, we came up with a far less complex design involving only a hobby servo. To control the speed of the motor and servo, we wired potentiometers to allow for fine-tuning by the user. We did this because the senior design team provided us with a range of speeds at which the filament would be coming from the extruder. Integrating adjustability into our design also ensures that the filament would not be distorted by the spooling process. After completing the modeling process on paper and selecting the components that we would like to use for our project, we turned to SolidWorks to create a 3D model of our entire apparatus. We did this by creating one main assembly and a smaller sub-assembly which consisted of the mounting bracket that actually printed in two pieces. Shown here is our completed 3D model. At the left side of the base, you'll notice a white piece of tube slid through the wood. This is actually a piece of 1.5" diameter PVC pipe that we found at the local Ace Hardware. The main function of this PVC pipe is to support the weight of the spool and also provide a quick attach and disattach system for the spool. What isn't shown is the U-bolt that we use to attach the left side of the PVC pipe to the piece of wood. After completing the modeling process in SolidWorks, we saved the printed parts as STL files to be used with the MakerBot 3D replicator. After printing the parts, we noticed a fair amount of distortion in the mounting bracket from the spool to the motor itself. This did not prove to be a problem, however, because the mounting bracket still served its basic function. After we printed the parts that we needed on the MakerBot 3D replicator, we moved to fabrication. We started by mounting the DC motor in a piece of wood shown at the right. After that, we glued the mounting bracket together, which came out in two pieces off of the MakerBot replicator, and then mounted this mounting bracket to the motor itself. After mounting the motor to the base, we moved to the right side of the base to mount another piece of wood to support the piece of PVC pipe. We first drilled a hole in this piece of wood to allow the piece of PVC pipe to slide through. After that, we drilled two holes on the left and right side of this hole to allow for the U-bolt to slide through. The U-bolt slid into a notch in the back of the PVC pipe that fastened it to the piece of wood so that it wouldn't move. This provided a fixed resting place for the spool and also supported the weight of the spool so that it would not place any extra stress on the motor. After the basic fabrication of the base itself was complete, we moved to some of the more minor details. This involved cutting holes to clear wires, mounting feet to the bottom of the base so that it would clear the hardware that was mounted in the base itself, and installing a metal tube to protect the wires running to the DC motor. In the final stage of fabrication, we painted the two pieces of wood mounted to the base white, and also organized the wires underneath the base itself so that we could find them easily when we went to program the Arduino. After fabrication of the mechanical components was complete, we moved to program the Arduino to work with our components. We began by getting the motor to turn with a basic Arduino program shown in the examples. After this, we wired up a potentiometer to control the actual speed of the motor. We did this using the analog inputs and the potentiometer already mounted to the base of our prototype. Next, we wrote a code to control the speed of the servo. We did this by wiring the potentiometer to an analog input. Next, we use this input to control the delay on the servo. This actually controls the amount of time the servo waits before it moves to the next position. By doing this, we knew that we could control the speed at which the servo swept across the face of the spool. The results from testing reflect the effort and time spent during the planning process. Our final prototype was able to turn the spool without any issues and distributes the filament evenly across the spool as it turns. Our prototype is capable of spooling the material at a rate of 3 inches per minute all the way up to a rate of 35 inches per minute, which well exceeds the senior design team specifications of 5 inches per minute to 10 inches per minute. A video of our design functioning can be viewed by following the link displayed on the screen. Our group performed well in most aspects of this project, but we could have used our resources more efficiently. We should have talked to more people around campus to locate the proper tools needed to complete the fabrication of our final design. Instead, we made do with the few tools that we had access to, and the end result is a good functioning design, but a little bit unorganized. Overall, we learned a lot about design, fabrication, teamwork, and combining these aspects to create a product that fits the needs specified. We gained several skills that will help us in senior design. The most important of them all is the ability to create a math model for any given situation. This skill will not only be useful in senior design, but also in the workplace after we graduate. Thank you for watching.